things on the topics list. So we're going to look at something called cylindrical coordinates today, and spherical coordinates tomorrow. These cylindrical coordinates are just a 3D extension of polar coordinates that we may or may not have seen before. Regardless, we are going to review polar coordinates together. Raise your hand if you've never seen polar coordinates before. Cool, all right. But again, we're still going to have a chance to review it. These next two lessons should belong in that first unit where we're just talking about how does 3D space work. But just to avoid a super lengthy exam, I just kind of squeak them into the second unit. But this is still just getting used to understanding things in 3 dimensions. So right now, if we talk about polar coordinates, we are in 2 dimensions. So we have the regular XY plane that we have always seen before, and we can call this the Cartesian plane. Also just known as the rectangular plane. This over here is what we have always seen before. Yes, this is still in our team. And we define coordinates in this plane. I could give you a point, and we always just said, oh, okay, that means you move to the right some x distance, very positive number, then you move up some y amount. And that gives you a point in the rectangular plane. So polar coordinates is just another way of expressing a point that is defined by 2 things. So when we talk about a point, we are now going to refer to that not as x comma y, but as some r comma theta, where r is the distance to the, we don't call it the origin here, we call it the pole. So r is the straight distance to the pole, and theta is the angle in standard position. Standard position, one more time, means from the positive x-axis going counterclockwise. So on that sheet that I passed around, these are examples of polar planes. And they're concentric circles. So each circle is going to be like an R value. So an R value of 1, R value of 2. And then these angles here are just to help us kind of stay organized when tracing out our angles. So I could ask you to plot the point 2 comma pi over 4 in the polar plane. So this is saying you can go out a distance of 2, and what you're seeing on your polar plane now is you are going to live on that circle with a radius of 2. You're going to travel around that circle until you get to an angle of 45 degrees, or excuse me, sorry, pi over 4, which is 45 degrees. And this represents the point 2 comma pi over 4. So I'm going to give you a list of points. We're going to go ahead and sketch all of those points in the same plane, just to save space. So go ahead and plot points A, B, C. Did I give you guys a unit circle?
No.
Yeah. No. 2, 7, 5, 6. Unit circle. Put your one somewhere. Three. 1, 2, 3. I have 3 pi over 2. Not 2 pi. No, 3 pi over 2 is way down here. Down here. How's that gonna work? Oh, 3. 2 is good. Oh, so it's 1, 2, 3. 3 pi over 2. It's here. Not 3.
There are 2 there. Okay, so when I say we'll need a really, really good understanding of the unit circle, yes, the coordinates, like we did in pre-calculus, but really the biggest thing is just understanding how angles work. And I'll play around with that in just a second to really show what needs to be exercised when we think about these angles.
How's that gonna work down? Okay, so you are going, okay, so about 3.
How do we feel with A and B so far?
Yeah.
Let's do C together. So C, you can have a negative radius. The same way that in the Cartesian plane, you could have negative x coordinates. Because it feels kind of weird. It's like, oh, well, it's the distance that you move over to the right. Same idea, it's just the distance that you're gonna move over to the left. So, two ways of thinking about it. You could say, this is go out to a radius of -2, and then from there move with an angle of nothing. Or you could start at an angle of 0, which is the positive x-axis, and then just move 2 to the left. However you want to think about it, you'll land on the same spot. Just so showing there, you can have a negative radius. You also can have a negative angle. We'll plot some of those in just a second. And then lastly, 1 pi over 2 would be that. How are we writing? Yeah. You could have, so you would have a sheet. You can just have a sheet. So something you just want to kind of just jot in your notes and remind yourself, in the polar plane, not all points are unique. So if I ask you to plot A, which is 2, 3 pi over 2, and B, which is 2, negative pi over 2, I'm going to go out 2 units, go to an angle of 3 pi over 2, that's A.
2 units. And yeah, negative.
And then 2, and then just negative pi over 2 is now going in the clockwise direction. A and B are the same point. So just remembering that not all points are going to be unique in this kind of. Give me other coordinates that are equivalent to A and B.
One, 0, 1, 2, 5.
Hang on, those would be,
Oh, it'd be on the same point.
yeah, you want to be on the same point as A and B.
Oh.
But I agree that yours are equivalent.
-2,
You said, so -2, and then what?
And then 3 pi over 2.
That would put me over here though.
Oh.
So -2
Negative
pi over 2.
pi over 2.
There's another one. What if we go to pi over 2 and then have a radius of -2?
Radius.
Oh, I just said the same coordinate twice.
Yeah.
Um,
So that's how to plot the points. The next idea that we want to get comfortable with is how to convert the coordinates. So converting polar to Cartesian or rectangular. So we're going from r comma theta to traditional x comma 1. So this is just something that goes in our toolbox. X is equal to r cosine theta y is equal to r sine theta. And lastly, r squared equals x squared plus y squared. So again, something that goes in our toolbox, we've just got that locked in and memorized. I will take 2 seconds and just kind of show you where they come from, not something you would be responsible for. And if you have this polar picture here, you could just think of this as being a right triangle. And if you want the x-coordinate, or how much you've moved from the origin over to the right, then using some trigonometry, you could say, oh, well, I recognize that the cosine of that angle is adjacent over hypotenuse. So if I wanted to solve for x and just multiply both sides by r, you get r cosine theta. Similarly, if you said, oh, we'll call this y, you would land on r sine theta. And then lastly, because this is now a right triangle, it needs to be true that a squared plus b squared equals c squared. Well, there it is. It needs to be true that x squared plus y squared equals r squared. So now I'm going to give you some polar coordinates. And we're going to convert them to rectangles. And what better way to do it than to take the points that we already have and convert them to rectangular coordinates. So what is our final answer going to look like here? We're going to get something different than this, but position in the plane will be the same. So A should still be this point here. And without even touching the marker to the board just yet, what should the rectangular coordinates of A be?
Rectangular.
0, -3.
0, -3. So now, let's actually see if this holds true. Remembering to find the x comma y, you're going to say the x coordinate is r times cosine of theta. The y coordinate is r times the sine of theta. And we know that we should land on 0, -3.
Like, okay.
Now let's do this going down this. some of these that live on the axes should be pretty easy to check. Other ones, like maybe point B, it's not entirely clear if I did it right. However, I know I'm at least in the right quadrant. A negative x and then a negative y. So I'm at least in the right quadrant. Things that live on the x and y axes are going to be pretty straightforward. Like point C should be the point negative 2, 0. Check. D should be 0, 1. Looks great. And then we did A together, but that's 0, negative 3. So if you want to convert from polar to rectangular, or polar to Cartesian, same thing, then this is the toolbox that we need. X is r cosine theta, y is r sine theta. And if you ever see an r squared running around, we can just translate that to x squared plus y squared. Now let's talk about going the other way. What if I give you a Cartesian coordinate and we want to convert to polar? And I do have a printout once we're finished with all of them, that'll have all the things that need to go in our toolbox. So something that just goes in our toolbox. R is the square root of x squared plus y squared. Theta is the arctangent or inverse tangent of y over x. And then x squared plus y squared equals r squared. If you're looking at this going, wasn't this the same thing we had last time? Yes, it is. Only thing I wrote last time was r squared equals, now we can just write as x squared plus y squared equals r squared. It's the same idea though. So very quickly, again, I'll just kind of show you where this comes from. Yeah.
Is arctangent just cosine over sine?
No, that would be cotangent.
Oh,
This is the same thing as inverse tangent.
Inverse tangent, arctangent.
is there like simplification in cosine?
Mm-hmm.
No.
No.
You're thinking of cotangent,
Yeah.
which is cosine.
Yeah.
So just again, a quick justification as to where this comes from. If you've got some x and some y, then we're defining r to be the distance from the origin or from the pole. Well, this distance is just the hypotenuse of a right triangle. So x squared plus y squared equals r squared. Oh, well then solving for r is equal to just the square root of x squared plus y squared. And we want theta to be this angle here. Well, if this is my x, that's my y. It needs to be true that tangent of that angle is opposite over adjacent. Therefore, that angle is arctangent y over x. Again, just showing where they come from. We're not responsible for reproducing those. So now I'm going to give you some points in the rectangular plane, and we're going to convert them to polar coordinates. So I have in rectangular coordinates 4, -4. The goal is to now write this as a polar coordinate. I'm just gonna look at my toolbox. This says that r is the square root of x squared plus y squared.
It's 32. Square root of 32, right? Break it down. 15 and 2. No, 4 and 8. Square root 2, 8. Okay. Wait, one more, yeah. 16 and 2.
So square root of x squared plus y squared, that's 16 plus 16. If you said just square root of 32, that's fine. If you said, oh, well, I recognize that could be simplified in 4 root 2, sure, we're on the same page.
Okay, yeah. 42.
And now the angle is equal to arctangent of the y coordinate divided by the x coordinate.
Right. Yes.
And this is kind of the same idea that we were talking about with the arc length last class, as far as sometimes it'll be a nice clean answer. But if the question says something like round to the nearest tenth, this arc tangent, you'll just have to whip out a calculator and get a decimal. Now, for some of the ones I'll show you today, we'll make sure that we understand the unit circle. This is saying arc tangent of -1. You have to ask yourself, where on the unit circle is tangent, so the y coordinate divided by the x coordinate, -1.
Ooh. I don't know. So, I think it would be in either the first or the fourth quadrant.
Tangent would be positive in the first quadrant.
No, I mean the second or the fourth quadrant.
Yes,
Excuse me.
yes. So it's in quadrants 2 and 4.
Oh, so okay.
Well, hang on. If y over x gave me 1, or -1, then that means the coordinates need to be the same, just off by a sign. And what angle does that have to have?
Where they're the same. Oh, 2 squared over 2.
So those are the coordinates, totally agree? What angle is that?
What angle is that? That is that pi over 4? No.
But in quadrant 4, that's 7 pi.
7 pi over 4. Oh, okay. Ah. Hey.
So where is so arctangent is saying where is tangent? Where is the y coordinate over the x coordinate? -1. Well, if I got 1 or -1, that means the coordinates need to be the same, just off by a sign. So that when I divide them,
6.
I just get -1.
Where is 7? So that's in the fourth. The fourth.
But here's another good thing to mention.
3 pi over 4.
Arctangent of -1, you also could have said, in quadrant 2, you could have said 3 pi over 4.
Right.
But this is where we just need to pay attention to the problem a bit. I want the point
Where y is
that
negative.
is in the fourth quadrant. So don't give me the angle over here, just give me the angle in the fourth quadrant.
Right, where your y is negative.
So if you wanted to think of this in polar coordinates, this is saying go out a little bit past 4. But now we're going to go all the way around the circle like this. And now if we're thinking, well, I'm kind of confused as to why it would be past. If you wanted to think of this geometrically, this is a triangle with length 4 and length 4, so distance. Then the hypotenuse of that 45, 45, 90 triangle would be 4 root 2. Yes, we're gonna do that on this.
Ew. I know, right? That's ew.
Oh, hang on, before we even talk about this one, let's look back at the last one, there's one more thing I want to mention. So we do want to write this as one final coordinate, 4 root 2, 7 pi over 4. But that is not the only coordinate you could have given me. Because right now, this is saying go out 4 root 2 and go around at an angle of 7 pi over 4. But what is another coordinate that you could have given me that represents that same point?
You can go -4 square root 2,
Okay.
and then
Whatever this angle is.
yeah, that's
True.
at least
How about this? Still go to the right
okay,
4 root 2,
and then go down.
which would be what angle?
What angle? That's 0. Right, 0 and
Negative pi.
pi over 4. Okay.
So that's kind of the idea that I'm talking about. It's not really going to hurt us in this unit, but in the next one, we need just a profound understanding of how these angles work. We're going to have to just be able to translate left and right. I'm not going to call this 7 pi over 4, 7 pi over 4. I'm going to call this the angle negative pi over 4, just going in the opposite direction just a little bit. So these two coordinates are the same. Alright. I'll give you guys a 45-second head start to try this one. Convert from rectangular to polar.
Yeah.
So we get a radius of 3, and I get arctangent of 3 over 0. That's undefined. Okay, so I'm just asking myself, where is tangent on the unit circle undefined?
In the tangent, I don't know about tangent. I don't know arctangent.
You can think of it as just saying, where on the unit circle do you take the y coordinate, divide by the x coordinate, and get something undefined? If you get something undefined,
Pi over 2,
say again.
pi over 2,
There's another one.
and
3 pi over
3
3 pi over 2.
Yes, pi over 2 and 3 pi over 2.
Right.
But which one do I pick? You just look back to the original point and go, okay, well, if I want 0, 3,
You want pi over 2.
I want the pi over 2.
Mm-hmm.
So my final answer is this point can be represented as r comma theta, so 3 comma 3 pi over 2. good there, or do we need to see one more? See, let's do, let's do one where we would need a calculator.
Okay.
Reviewing polar coordinates.
Yeah, I'll do that. Fours and threes, gotcha.
So this just came in straight from the calculator. You got arc tangent. But we need to pay attention. We actually saw this idea come up when we talked about vectors already. What is wrong with what the calculator gave? It's not bad. Because we can have negative angles, it just means you go down to negative 48 degrees.
Right.
The angle's in the wrong quadrant.
Say again?
The angle's in the wrong quadrant.
It's the angle's in the wrong quadrant. If you think about where we really want to end up,
-7.
negative 7, 8.
Right.
Uh-oh, my calculator is giving me an angle here,
Right. So you have to add 180
so
to
you
it.
add 180. Don't forget, by default, arc tangent is always going to give you angles in quadrants 1 and 4.
Right.
So to get to the other two quadrants, we need to be able to add 180. We have to pay attention to when that happens. So after adding 180, now this is going to give me the angle level.
Right. Something. 31 or 31 something. Yep.
And now, we've actually seen this before. We saw this both times already. When we saw arctangent as -1, we did get two different answers. We got the answer in the fourth quadrant and the answer in the second quadrant. Since we're looking at a unit circle, we kind of just pick. But since the calculator is just forced to give us one, the calculator will only give you answers in quadrants 1 and 4. You just have to remember, okay, I need to do that extra step to get the ones in the other quadrants if needed. So that was just how to convert points, simple coordinates, how to, translate between the two different worlds. Where we really want to get to by the end of this class is being able to work with functions in these kind of coordinate systems. And then, yes, derivatives and integrals, things like that. So maybe something to just help us think about what things look like here. If I want to convert from rectangular to polar, then I'm simply just going to look at that toolbox. And I remember that x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So if I want to convert y equals 5, then I'm just going to say, well, y is equal to r times sine theta. A good question. How do you know when you're done? You're done when you don't have any more x's and y's. It is the simplest answer. But we're always going to try to write our answer, if possible, as r equals something. So yes, technically you're done because there are no more x's and y's. There are now only r's and thetas. But to solve for r, you could divide by sine theta. And 5 over sine theta, or 1 over sine, is cosine.
Ah, right.
X equals 2, same idea. X is equal to r cosine theta. True, I agree you're done, but let's solve for r. And what is 1 over cosine equal to? C.
Secant.
So, before we even touch pencil to the paper for this one, don't forget we're living in R2. What does x squared plus y squared equals 4 look like in my Cartesian plane?
Circle with radius 2.
Circle with radius 2. Again, before I even touch the pencil to the paper, how would I describe that in polar coordinates? True. But since my coordinates are represented as r comma theta, this is gonna be all points on the circle that have a radius of 2.
Right.
Okay, so I know where I wanna end up. Ah, here it goes. X squared plus y squared, I can just make a substitution that is r squared.
What, 2 squared? Okay, yeah.
And if I take the square root of both sides to solve for r, then you get just r equals 2. And there you go. It's kind of important to be able to recognize, if I gave you y equals 5 in the Cartesian plane, we know that represents the horizontal line at 5. And x can be anything. Well, if I give you r equals 2, that means anywhere with a radius of 2 is fair game, and the angle could have been anything. So if I asked you what does r equals 2 look like, you should just recognize this is a circle with radius 2 in the point.
Hmm.
How would you write the polar coordinate for like a circle and radius of 2?
Say that one more time.
How would you write like the polar coordinate of the
So this is not a polar coordinate, this is a polar equation. It's
Just a
all
radius.
points that have a radius of 2.
Okay.
Very similar to how over here, y equals 5 was all points with a y coordinate of 5. Alright. Let's go the other way. What if I give you a polar equation now?
Polar, change rectangular. It's radius of 3. So,
This represents, in the polar plane, it's saying no matter where you go, the radius is 3. Without using any intuition, just using substitutions that we have from our toolbox, I can just square both sides of the equation.
okay.
I can just say, square this side,
9.
square that side.
So x is 9.
And now I'm ready to make my substitution that, that's right, r squared is just x squared plus y squared.
Equals 9. Okay. Hmm. So it's 3.
This next one is r equals 4 cosine theta. I look over at my substitutions and I don't know, because I need r squared to plug in x squared plus y squared, and the cosine piece I need an r. So it's almost like you need an r on both sides. So why don't we just multiply both sides by r? Aha. R squared is in my toolbox, and so is r cosine theta. R squared is x squared plus y squared, and r cosine theta is x. Now, you could rearrange this. It would just be a lot of algebra completing the square. You can move this over and end up writing this as something. This just ends up being a circle. It's just not centered at the origin. It's just moved over a bit. Let's see if our intuition tells us. What if I have the equation theta equals pi over 4? What would that look like in polar coordinates? It means that theta is pi over 4, and the radius could be anything. So what does that end up looking like?
Radius. Guess you have to go out at
Second?
an angle of pi over 4 first.
Okay. And then the radius could be anything. Could even be negative. So what shape am I getting?
A line.
You get a line. So in polar coordinates, if you have just angle equals, you get a line. So if you have r equals, circle, angle equals, you get a line. But let me actually show you some substitutions of how to actually get there. In our toolbox of converting, we also had theta equals arctan y over x. Well, I'm just going to make a substitution that theta is equal to arctangent of y over x. In rectangular equations, we usually have it as y equals something. So I'm going to take the tangent of both sides. And tangent of arctangent y over x is equal to y over x. What is the tangent of pi over 4? Meaning I whip out my unit circle, go to an angle of pi over 4. What is the y coordinate divided by the x coordinate?
Y coordinate, that's in the first quadrant. Square root 2 over, square root 2 over 2, square root 2. Oh,
So I agree it's square root 2 over 2 divided by,
square root 2 over 2.
but anything divided by itself
Right, it is 1.
is
Yeah.
So tangent of pi over 4 is just 1. Well, if I want to solve for y, I get y equals x. And lo and behold, y equals x. There it is.
Would that always be like that if you're just giving?
If it's pi over 4. If I change this to pi over 6, you would get an angle with a different slope, but still no y intercept. It would always be y equals something. And it's really going to end up being what is the tangent of that angle that I'm giving. Questions?
I like that.
Alright. That was just a review. However, extending it to 3D, you guys are going to love this. It's super,
Yeah.
super simple. The only hard, quote unquote, hard part about this is the actual polar coordinate part. That's why I spent some time doing the review there. So we are looking at cylindrical coordinates, which is just the extension from 2D to 3D of the polar line. So give me 2 seconds while you stare at that. I'm going to attempt to draw this on the board. So extending this idea to 3D, when we looked at 3D points in our rectangular world, it was still you go over in the x, over in the y, up in the z. The first two components of this coordinate are still r and theta. So it's going to be how far you go out of a radius, how much of an angle that you travel in the xy plane. So this is my theta, the angle from the positive x-axis sweeping towards the positive y-axis. The radius is still the distance from the pole, but I want to be super clear that, despite my horrible drawing, all of this lives in the xy plane. Everything is flat. The last part of our coordinate is z, which I promise you guys are going to love this, is the same z. That's it. So extending it to 3D is really just normal polar coordinates. Tell me how high I have to go. So we get this idea of quote-unquote cylindrical coordinates because you're going out and sweeping and just going straight in.
So z can never be negative.
Sure can. It would be the same thing as going out, sweeping,
Damn.
going in.
Okay.
So, but again, cylindrical coordinates, which is the new piece for us, really is just hanging on to the polar coordinates. So if we're shaky after today's lesson, I promise we're shaky on the polar coordinates, not so much the cylindrical stuff.
Okay.
But we still want to practice converting them. And notice the toolboxes seem familiar. R is equal to the square root of x squared plus y squared. That's because R still lives in that xy plane, has no kind of height to it. Theta is arctan of y over x. And I put it just for emphasis, z equals z. Just to remind us that there's no conversion there. Z is going to stay the same. X is still r cosine theta. Y is still r sine theta. And z equals z. All right, let's convert some points in there. So now this is where we shift in the lesson. Now we're in 3D. So we're not going to call these polar coordinates, we're going to call these cylindrical coordinates as we're improving. We're converting from cylindrical, so we're going from r, comma, theta, comma, z to rectangular x, comma, y, comma, z. Right off the bat, the z coordinate is going to be the same. So I already know in my final answer over here, my coordinate is going to be something, comma, 4. The z is the same. I just look at my toolbox, and I go, okay, that's right. X is equal to r cosine theta. Y is equal to r sine theta. I look at my handy dandy unit circle. The cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is 1/2.
Nice.
So now, that is my x coordinate. That is my y coordinate, and again, the z is z. That's it. Thinking about this point in cylindrical coordinates, it's saying go out a radius of 5 along the positive x-axis. Sweep with an angle of pi over 6, and then from that point, go straight up. Just making sure that makes sense, it's saying go out some positive amount, towards the positive y some amount, and go up. You still live in that same first octave. So r is the square root of x squared plus y squared. That's the square root of 4. Nice, that's just 2. I get arctangent of y divided by x. Square root of 3 over 1 is square root of 3. Now, we should just have this kind of locked in. So on your unit circle, we know that the tangent of 0 is 0. We should have that the tangent of pi over 6 is y divided by x. You get square root of 3 over 3. Tangent of pi over 4, 2 coordinates divided by itself is 1. And tangent of pi over 3 is root 3. And then you get symmetry in the other quadrants. Now, this isn't too crazy. Say this is multiple choice and you land on arctangent of 3, you plug that in your calculator, you would just get a decimal approximation for pi over 3. This is just nice because you can write it as an exact answer. So my final answer would be r comma theta comma z6. last thing I want to talk about are now equations in cylindrical coordinates. Well, let's talk about what would it mean if you had r equals something? What would it mean if you had theta equals something? What would it mean if you had z equals something? So if you had r equals 5 in cylindrical coordinates, that's saying no matter where you go, you always just go out 5. What kind of surface does that represent in 3 dimensions? It's a cylinder. You're allowed to go out 5 in any direction, but also at any height. So r equals something is a cylinder. How could I have seen that if you square both sides from your toolbox, x squared plus y squared equals 25, boom, there's your cylinder. How would I see theta equals pi over 3? If I go out an angle, I'm allowed to go out any radius and also with any z coordinate.
That is
There's your plane. So this is a cylinder. Plane.
But that's a cylinder in 3D, right?
Correct.
Okay.
And now z equals something. This should feel familiar because z is still z. This is saying no matter where you go, you have a z coordinate of something. Also a plane. Because z stays the same idea, this is still a plane.
That question, that z equals 8 is perpendicular to your x and y coordinate.
X, y. Say that one more time?
It's perpendicular or orthogonal to your x and y coordinate. That z equals 8.
Parallel.
Parallel. It's parallel. Ah, okay. And then the angle theta, pi over 3, is that just in all planes?
So if you give me angle equals something, this in cylindrical coordinates will represent a plane.
Plane, okay.
And I'll just show you a quick substitution here. Theta is arctangent of y over x. Take the tangent of both sides. Tangent of pi over 3 is root 3. And in 2D, this is a line. In 3D, that is a plane.
Plane.
So theta equals anything will always be a plane.
Okay. Gotcha.
I do have practice problems. I will probably try to post more practice problems. But this is just one of our systems that we can live in. The next time we're going to talk about spherical coordinates, which is just another 3D representation of how to represent points in physics. I can't believe it, it's Wednesday already. That means Friday, we're going to do a retake. If you would like, I will be in my office tomorrow from 1:15ish to 2.
1:15 to 2. That's tomorrow. Okay. Oh, that's cool. I can come see you tomorrow. 'Cause I have class at 2. All right. Cool.